The James Webb Space Telescope, JWST, has uncovered surprising new discoveries about the very early universe that challenge what we previously understood about the Big Bang. For decades, scientists have worked to explain how our universe began through the well-established Big Bang theory. This holds that approximately 13.8 billion years ago, the entire observable universe was condensed to an incredibly hot and dense single point, which then rapidly expanded and evolved over billions of years into the cosmos we observe today. While this theory fit observations very well, it did not explain what could have existed or occurred prior to this massive expansion event. The JWST was designed to help answer this perplexing question by observing the most distant, observable objects in the young universe. Its recent findings have now thrown astronomers a true cosmic curveball. Observations of extremely ancient galaxy clusters and individual galaxies have pushed back our view of the early universe even further, to within the first billion years after the Big Bang. This suggests that some processes we did not previously account for may have been at play in the earliest moments and preconditions of the universe. The JWST is truly reshaping our understanding of cosmology and how it all began through its revolutionary views deeper into the early days of space and time than ever before. Scientists have long puzzled over what could have existed or occurred prior to the immense explosion of energy we call the Big Bang. While it beautifully explains how the universe dramatically expanded from a hot, dense state, the Big Bang theory itself does not account for what kicked things off in the first place. To address this gap, astronomers have proposed several intriguing hypotheses for what may have come before. One idea is the Big Bounce theory, which suggests our universe is just the latest in an endless cycle. In this model, the current expansion will eventually slow and reverse, collapsing everything back into a singularity which then bounces to trigger a new Big Bang and subsequent universe. Quantum gravity theories suggest spacetime can bounce at high densities, avoiding singularities. Loop quantum cosmology also predicts a bounce as the universe contracts. Another proposal is the ekpyrotic scenario, where our cosmos emerged from the collision of two immense brainworlds in a higher dimensional space. This high-energy impact could have set off rapid inflation, smoothing out irregularities to seed the structures we see today. String theory includes higher dimensions that could host colliding brainworlds. Some brain collisions in computer models produce inflationary expansion resembling our universe. The pre-Big Bang scenario paints a picture where the early universe transitioned from a low-curvature, low-energy state into one of high curvature and high energy through a period of superinflation. Early universe equations have multiple solutions, with one transitioning to another via inflation. This matches predictions of string theory for a pre-Big Bang phase transition. Finally, the no-boundary proposal contends that the universe has no edges or boundaries in space and time. The Big Bang was simply a smooth transition when its size became minutely small, birthed from a quantum fluctuation determined by the universe's wave function. This proposal is supported by theories unifying quantum mechanics and general relativity, like Euclidean quantum gravity. These suggest the universe can emerge from a regular instanton without an initial singularity. The cosmic microwave background matches an inflationary universe, and its fluctuations could have seeded from pre-Big Bang perturbations. The universe appears geometrically flat and homogenized, as inflation predicts. Dark matter and dark energy observations also align with inflationary models, and the universe's age, composition, and structure generally fit a hot Big Bang, followed by inflation and structure formation from gravity. Each theory offers a unique perspective on what strange realms could have existed before the beginning of our known cosmos. The James Webb Space Telescope has revolutionized our view of the very early universe in the short time since its launch, making discoveries that have astonished astronomers. Among its most significant finds was detecting the furthest back protocluster of galaxies yet, a hugely important glimpse into how the cosmic structures we see today first began to form. On the largest scales, galaxies are not uniformly distributed throughout the universe. Instead, they exist in enormous filamentary structures called the cosmic web. The cosmic web consists of dense clusters and superclusters of galaxies connected by thinner filaments. These filaments intersect to surround immense void regions, largely empty of galaxies. The web is believed to have formed as a result of variations in density and gravitational pull in the early universe acting on dark matter. Regions of slightly higher density dark matter attracted more material. Over billions of years, the initial pattern set by dark matter evolved into the large-scale structure we see today, with galaxies and galaxy clusters arranged in a web-like network spanning the observable universe. Maps created using galaxy surveys reveal the intricate patterns of the cosmic web, which bears resemblance to the cracks in dried mud or patterns formed by bubbles in foam. Studies of the web provide clues about the growth of structure from the initial fluctuations after the Big Bang to the distributions of galaxies, galaxy types, and galaxy clusters across space. JWST's observations of early protoclusters and galaxy distributions are starting to trace the very beginnings of this structure emerging from the initial conditions set in the early universe. So in essence, the cosmic web describes the interconnected, network-like arrangement of matter at the largest scales governed by dark matter and gravity over billions of years of cosmic evolution. Dark matter is believed to make up about 85% of all matter in the universe. Though it doesn't interact with light, it has gravitational pull. Slightly denser concentrations of dark matter were able to attract more matter shortly after the Big Bang due to their extra gravitational influence. Over time, these small initial dark matter density fluctuations grew larger through their own gravity, creating a web-like pattern of dense clumps and filaments. Ordinary matter like gas was drawn into the strands and knots of this emerging dark matter scaffolding structure. Dark matter acted like the skeleton that provided the infrastructure for the cosmic web. Its gravitational influence determined where matter aggregated on large scales. Regions with slightly more dark matter evolved into the earliest galaxy clusters, while less dense regions became the voids we see today. Ongoing simulations of dark matter evolution continue to shed light on how its complex interactions shaped the assembling superstructure we observe billions of years later. Even 650 million years after the immense explosion we call the Big Bang, the universe was still in its earliest stages, a time when it had only cooled and expanded enough for the first light from newly formed stars to begin illuminating the darkness. Yet within this infant cosmos, JWST uncovered a collection of 7 fledgling galaxies, verified to exist at this record-breaking early epoch. While still diffuse and not yet gravitationally bound into a proper cluster, here was clear evidence that individual galaxies had come together in the same region of space, suggesting the very first steps towards clustering and the birth of superstructures. At a time when the universe comprised not much more than hydrogen and helium glows, it was astonishing to find any association of multiple galaxies at all. This protocluster discovery challenges ideas around how quickly galaxies could have come together and how the seeds of larger clusters may have been sown even in the universe's first billion years. JWST's vision has profoundly impacted our view of this formative early period and how rapidly structures began emerging from the primordial chaos that reigned after the enormous expansion of the Big Bang. To help comprehend just how early this is, we need to think about the immense age of the universe. The Big Bang occurred approximately 13.8 billion years ago, so this protocluster dates back to a time when the universe was still in its absolute infancy, less than 5% of its current age. At that point, the universe had only just begun forming its first bound structures through the force of gravity. Individual galaxies were only starting to take shape within the diffused gas and dark matter that filled the cosmos. Yet somehow, within this ultra-young universe, the JWST uncovered a collection of galaxies that were already beginning to gravitationally cluster together, the earliest example of such a group found to date. This revolutionary find provides a glimpse into how the first generation of galaxies may have started aggregating into the large-scale clusters we see today. It shows that even in the universe's tender first few hundred million years, the seeds were being sown for the cosmic web of galactic superstructures we observe across the present-day sky. This extremely early protocluster discovery by JWST has some important implications for our understanding of galaxy formation. It shows that galaxy clustering and the formation of large-scale structures was already beginning much earlier than we previously thought. This suggests the initial fluctuations that seeded galaxy formation after the Big Bang must have occurred even earlier. The fact that galaxies were able to gravitationally associate with each other so soon after the Big Bang implies that the very first galaxies may have formed earlier than models predicted. They would have had time to start clustering in this young universe. It provides evidence that the hierarchical model of galaxy formation is accurate, where smaller structures like galaxies formed first and then merged together over time into larger groups and clusters. We're seeing this process starting very early on. This protocluster was already fairly massive, with the mass of many present-day galaxies combined. This early rapid growth is challenging to explain and may require revisions to galaxy formation theories. Finding such an ancient clustered structure suggests that large cosmic surveys have the potential to uncover even earlier galaxy populations, pushing our knowledge of the infant universe's evolution further back in time. This protocluster's record-breaking age indicates that structure formation must have begun earlier than expected, posing interesting questions for our theoretical understanding of galaxy origins. JWST has been unraveling the mysteries of galaxy formation in the young universe, revealing that clusters may have started coalescing earlier than expected. Through two other discoveries, astronomers have pushed back the frontiers of protocluster detection even further. One survey identified a collection of 4 galaxies within a small region of the sky, all dating to 1.2 billion years after the enormous energy burst we call the Big Bang. Though only a small group so far, analyzing their distances and motions confirmed these were the first example of a protocluster at this immense age. It showed that barely over 1 billion years since the beginning, gravity was already drawing some of the earliest galaxies together. This challenges notions of how rapidly structures emerged in the infant universe. An even more startling find came through another JWST observation, an incredible 7 young galaxies clustered within an even tinier patch of sky. Their spectra verified to shine from a time of just 650 million years after the primordial explosion. This pushed back the frontier by over 100 million years, an enormous amount in the context of early cosmic history. It provided a glimpse of some of the first multiple galaxies to form within the same small volume, the seeds of what would grow into today's immense galaxy clusters through the power of gravitational attraction. Both discoveries unveil surprising evidence that clustering and the assembly of cosmic structures may have commenced much earlier than previously hypothesized based on galaxy formation models. JWST is truly transforming our view of those first formative periods. One of JWST's most fascinating finds was a minuscule galaxy dating back an unimaginable 500 million years after the immense explosion known as the Big Bang. Despite forming so early in the universe's history, when it was still in profound darkness, this tiny galaxy was undergoing an intense burst of starbirth. Known as RxJ 212995, it resides at an enormous distance, corresponding to a time when the cosmos was but an infant. Yet through gravitational lensing and spectroscopic analysis, JWST could observe this distant dwarf was forming new stars at a rate matching even our own massive Milky Way galaxy. At a diameter over 3 times smaller, it showed an extraordinary concentration of stellar nurseries was already underway. Its lack of a visible supermassive black hole was also notable. Perhaps most intriguingly, the galaxy's intense star formation offers potential clues to one of the great cosmic mysteries, what ended the period of darkness known as the cosmic dark ages, when the universe contained no light. Its mini but mighty starburst suggests that the first generation of stars may have collectively provided enough radiation to ionize hydrogen gas throughout the universe, allowing light to finally travel freely for the first time. If more similar galaxies are found, they could have played a key part in illuminating the cosmos. JWST is poised to revolutionize understanding of how the darkness was dispelled in the early universe after the magnificent explosion that triggered the beginning of everything. One of the great mysteries astronomers seek to solve is what exactly brought an end to the prolonged period of darkness known as the cosmic dark ages. This was the time shortly after the Big Bang when the universe contained no light, as hydrogen gas had not yet become ionized across the vast cosmos. The discovery of the intensely star-forming dwarf galaxy, RxJ 212995, from 500 million years after birth of the universe, provides an intriguing new clue. Despite being only minuscule in size, It was churning out stars at an extraordinary rate. Yet perhaps most interesting of all, JWST detected no evidence of a supermassive black hole residing at its center. This was surprising, as many galaxies are thought to grow their massive black holes in step with the formation of their stars. The lack of a clearly visible black hole in such an ancient and distant galaxy suggests an alternate possibility for what ended the cosmic dark ages. Rather than radiation blasted out from growing black holes, the intense light from a multitude of newborn stars across many similar dwarf galaxies could have provided enough photons. If the early universe hosted numerous miniature star-making powerhouses like this one, their combined ultraviolet glow may have been sufficient to ionize most of the diffuse hydrogen gas permeating the cosmos for the first time. This would have lit the way for light to finally travel unimpeded. Further observations of very early galaxies are still needed, but this discovery indicates bursts of starbirth, not black holes, may have illuminated the long dark age after the Big Bang. But how exactly is JWST able to spot these ancient cosmic structures located billions of light years away? It starts with JWST's immense mirror and extremely sensitive infrared detectors, which allow it to observe much fainter and more distant objects than any previous telescope. Infrared vision is key, as the light from the earliest galaxies has been stretched to longer infrared wavelengths by the universe's expansion over billions of years. JWST then focuses on specific patches of the sky and conducts long exposures, gathering light from the faintest and furthest objects possible. Astronomers then use spectrographs to split the light into spectra, revealing signatures of specific elements that tell the object's distance and properties. By analyzing the spectra of multiple galaxies found within a small region of sky, JWST can determine if they exist at similar epochs after the Big Bang. If so, their proximity and clustering hints they are gravitationally bound into some of the first protoclusters. Through deep surveys across different areas, JWST is mapping out the locations of these earliest groups and clusters, glimpsing the seeds of the immense cosmic web of superstructures that threads the present-day universe. Its vision is unveiling how galaxy formation and clustering first commenced in the young cosmos. Mapping out the locations of the earliest galaxy groups and clusters discovered by JWST has some important scientific significance. It provides insight into the initial conditions of structure formation in the early universe after the Big Bang. Seeing where the first protoclusters existed can help constrain galaxy formation models. By pinpointing these protoclusters billions of light years away, astronomers can better understand how dark matter distributed and clustered over large scales at early times. This gives clues about the nature of dark matter. The spatial distribution of the earliest clusters can reveal information about the influence of dark energy on cosmic expansion and structure growth in the young universe. Comparing the locations of protoclusters to modern galaxy cluster surveys allows astronomers to trace how these large-scale structures have evolved and grown over billions of years through gravitational assembly. Mapping out the cosmic web of early clustering helps test theories about what generated fluctuations in the cosmic microwave background radiation detected by other observatories. It provides targets for follow-up studies using other telescopes to analyze the member galaxies, gas, and dynamics within these protoclusters in greater detail. Mapping these earliest clusters is critical for understanding structure formation and evolution throughout the history of the universe. There are a few key methods astronomers use to determine the age of the earliest galaxy groups and clusters discovered by JWST. Spectroscopy. By analyzing the light spectra of galaxies, features like the Lyman alpha absorption line indicate the redshift or stretching of light wavelengths due to the universe's expansion over billions of years since the light was emitted. This directly translates to an age. Hubble parameter. Astronomers know the rate of expansion described by Hubble's law. Combined with redshift data, this allows calculating the look-back time to the object, or how far back in time we are seeing. Additional targets must be identified through even deeper exposures to push our knowledge further back. And follow-up spectroscopy on more distant galaxy candidates will help confirm intriguing finds are truly as ancient as they appear. With more detections of galaxies and structures from the universe's formative periods, astronomers can start piecing together a more complete cosmological history. JWST has taken our view further back than ever, but many more observations lie ahead to truly illuminate the mysterious dawn of galaxy formation. So, scientists have considered to answer the following big questions after JWST's discoveries, such as: when and how did the first galaxies form? What were their masses, sizes, star formation rates compared to later galaxies? What processes drove the assembly of structures like protoclusters so soon after the Big Bang? What was the primary mode of star formation in the early universe, in isolated galaxies or clustered environments? How did cosmic ionization proceed as the first stars and galaxies illuminated the universe? What roles did supernova feedback and black hole growth play in galaxy evolution? What were the properties of the first generation of stars? Did they differ from populations seen today? When and how did heavy elements like carbon and oxygen first emerge? How did dark matter distribution influence early galaxy and cluster formation? What physical mechanisms governed the rise of metallicity and dust over cosmic time? Did the earliest quasars and black holes differ from their modern counterparts? To answer these pertinent questions, scientists are working on a new telescope known as the Large Synoptic Survey Telescope, LSST, which can help them address these issues. The Large Synoptic Survey Telescope, LSST, is an upcoming wide-field survey telescope designed to help answer some of the questions raised by the James Webb Space Telescope's recent discoveries. LSST has a huge primary mirror, measuring 8.4 meters or 27 feet across. It is located at Cerro Pachón in Chile and consists of a wide-field reflecting telescope with a 3 billion pixel camera. LSST has been designed to photograph the entire available night sky every few nights, capturing images of the sky in multiple colors. Over 10 years of operations, it will create a movie of the changing night sky and take the equivalent of a photo of the entire visible sky every few nights. LSST's wide field of view and frequent imaging capabilities will allow it to map the large-scale structures of the universe. Its data could help test theories around the expansion of the universe, nature of dark matter and dark energy, and whether structures in the early universe match predictions from theories like inflation. It may find additional very distant or old galaxies like those discovered by JWST. LSST's frequent imaging will allow it to detect redshift changes in galaxies, galaxy clusters, and quasars over time, helping clarify the nature and causes of cosmological redshift. This could help resolve issues raised about our understanding of redshift from JWST's data. Collaboration with JWST. By combining data from LST's large-scale maps with JWST's deep imaging capabilities, scientists hope to gain new insights into the early universe, structures formation, and cosmological models in light of the new telescope's revelations. So, LSST's unique survey capabilities have the potential to help address some of the major questions still outstanding from JWST's first discoveries. With a statistical sample of well-studied early galaxies, astronomers can begin to answer these profound questions about the formation and evolution of structure in the young universe. So, that's it for today's video. If you enjoyed the video, please consider by liking it and subscribe to this channel. See you in the next video.